So let's see. Okay, there's that. Oh yeah, and if you had your lab, go ahead and dump it up here, or if you forgot, you could dump it in on the break or whatever. Just up there is a good spot. Just turn it in before you leave. All right. All right, and the buffering's done. All right. Okay, and so I want to talk first about these terms, work and energy. And they're maybe just a little bit different than kind of the non-physics person's definition. Like when you talk about energy and having energy, you go to a club or something and there's a lot of energy in the club. That's not necessarily the same kind of thing. Or when you say, I got to get my work done, right? That doesn't quite mean the same thing in physics. So, work, I'm going to put a simple definition here. Now, there's a lot hidden inside of this simple looking definition. Oops. And I'm going to go into more detail on it. But for a physicist, work is some sort of an integral of force over distance. So in 1D, you can actually simplify this work, and I'm going to use a capital W so we can distinguish it from weight or omega. In the x direction, this would be the integral of f subscript x dx. Now think about this. Notice there's a dot product up here. If you were really motivated, you could imagine in 3D, you'd have three of these integrals. It'd be f sub x dx plus f sub y dy, etc. So that's what work is. It's an integral of the force over the distance. And at first you might be saying, this is fine, who cares? It's just some math trick. Well, I want to talk about kinetic energy as well. Now, for me, I think this will kind of work a little bit in helping you understand energy in general. For me, the more energy something has, the more likely it is to be able to kill you. So think about like hitting somebody with a rubber band, right? That might hurt them. If you pull it back farther, it might hurt even more. So the ability to inflict pain or damage is something about energy. Now, the letter we're going to use for kinetic energy, not very creative, we're going to use capital K. It's going to depend on some things. And I'm just curious if you want to try and guess what's something that energy might, if we're talking about kinetic energy, right? Kinetic makes me think of movement. What are some properties of an object that's moving that might relate to its energy, if you had to guess?
Velocity or speed.
Speed. Okay. And what else?
Acceleration.
No, it turns out that's not it. Interestingly enough, acceleration does show up over here, so they're going to be related. More on that in a minute. Mass. Which thing matters more?
Velocity.
Why? What makes you think that?
Because kinetic just like movement.
I like to think about it this way. Bullets have very small mass, but they can kill you because they're going really fast. Speed matters more, it's squared. If that doesn't work for you, okay, that's fine. But this is the equation for kinetic energy, all right? So for me, even small things like bullets can kill you and cause a lot of damage because they have such a large speed. So that's the equation. Yes, go ahead.
Or you could also think about how, like, when we have like stuff up in space, how we have like little individual particles that are going super really fast. We have to worry like to make special cushioning for them, because otherwise they'll just punch holes straight through our super heavy stuff.
Sure, sure. That's another good example, right? Even these tiny, seemingly insignificant particles with low mass, if you get them fast enough, they're extremely dangerous. Yeah, absolutely. So now at this point, I think I've got this shown here. So I'm going to do a derivation that's shown at the bottom of your page, and I want to show how these are related. You see that little caption that says deriving the work energy theorem? So my thought was, I don't want you to be writing anything down because you've got it written down. I want you to just kind of see how this relates to that. Now I'm going to skip a couple of steps here. Work is equal to, somebody already said this, force was equal to mass times acceleration. Right? But in this case, what's another way to write acceleration so that it relates to velocity? Meters per second squared, true, but what's another equation for a sub x that relates it to velocity?
Velocity over time.
Yeah, dv dt, right? Something like that, which is this, okay. Now I know this seems a little contrived, but just hang with me for a second. Seems like we're just playing around with a bunch of symbols, but there's a really interesting result that's going to show up. We get mass times dx. Okay. Now that these are differentials, some of you maybe feel a little bit uncomfortable about this, but when you have differentials, you can literally reorder them, right? It's just like normal fractions. Like if it was 3 halves and 7, you could switch the 3 and the 7, so you'd get 7 halves instead of 3 halves. Now, for no apparent reason, I'm going to do that. And mass, I'm going to go ahead and factor the mass out. We're assuming a constant mass right now, so what the heck. We've got a mass out front. I've got a dx over dt just by switching the fraction around times ddx. Well, what's dx dt? Yeah. And what's the integral of v dv?
Would have to be somewhere.
So we get 1/2 mass v squared. Do you see it? Isn't that interesting? And then evaluated at initial and final or something like that, right? So in this case, I'm going to point out this is 1/2 mass v final x squared minus 1/2 mass v initial x squared. But that's just the change in kinetic energy. Isn't that cool? So there's something special about this too, compared to a lot of the work we've been doing. Is this a vector or a scalar? Right here. This is a scalar. There's no I hats or j hats. Even if there was on here, when you square it, that's doing the dot product with itself. We don't have to worry about that. Kinetic energy has no vector. Work, you take a force which has vectors, pick out the component that matters, and then get rid of all the vector stuff. This is going to be a scalar equation. This is a huge result. Let's bring it over here. We say work equals change in kinetic energy. Sometimes I'll use ERG for energy, just so you know, if you're wondering, that's sometimes my abbreviation for energy. It's an old physics unit. Said another way, work equals delta K. All right, that's called the work energy theorem. Now, in a practical world, what we're seeing here is this is something like the integral of f sub x dx equals, well, actually, let me write this out in full glory. All right. I'll get out of the way so we can discuss. This is actually the full work energy theorem if you wanted to do it. The idea is you could have some forces in the x, y, and z, and you get the work for each side separately, and then you add those all together. So in practice, for a great many problems that we saw last class, remember, or last few weeks, tension or normal force, those were constant forces. Do you remember that? Most of the time, they were constants in our problems. So look what happens if f sub x is a constant, right? It pops out. What's the integral of dx? x evaluated at initial and final, we get delta x. Does that make sense? If f sub x is a constant, I should write this first.
Do you need the initials and finals of those intervals?
Yeah, there'd be initials and finals here. Sorry. I get a little bit lazy sometimes. But if they're all constant, what happens is the force pops out and you get x evaluated initial final, which becomes delta x. Did that make sense? So we're going to get f sub x times delta x plus f sub y times delta y plus f sub z times delta z equals delta kinetic energy. That's another way you could write this. Good? All right. And finally, I should mention the last style of writing this. I'm trying to show you all the different styles of writing it. One technique is to split it into x, y, and z components. Another is to go back to the dot product. So I'm going to show you that one last time. If f vector is constant, work could also be described by this. In this problem, this is the dot product, right? And this term right here is the displacement. So for some reason, a lot of books, I see them using delta S for this particular equation. I don't know why. Kind of sloppy, hard to read. Think later. All right, displacement. All right, well, this is the equation you're going to use most of the time. I still want to emphasize it's only valid if the force is constant, okay? So for a lot of other classes, you may have to actually get out calculus. Some of you have probably done this one in your calculus class where there's that pit full of liquid under the surface, how much work is required to pump the thing out or something. Anyways, yeah. So there you might need to use some of this calculus. But for us, another way to write the dot product, does anybody remember? How do I get the dot product in terms of the vectors and their magnitudes? Does anybody remember how a dot product works?
AB cosine of theta.
AB cosine. So in this case, it would be force magnitude, displacement magnitude times cosine of some angle in between. And this happens to be the one we use most of the time. I introduced all that other stuff so you would know where it came from, what its purpose is, why it relates to energy. But from now on, we can pretty much just rock this equation out almost all the time. We'll have to do one or two problems with an integral, and I'll show you those later. Good? That's kind of an introduction to work and energy. Any questions about any of this before we keep rolling? Ready for an example, maybe? Ready for an exam? Okay, let's go. Yeah. All right. All right. I guess I'll say one last thing here. I know I've emphasized this already. Only valid when it's constant. This is displacement. So remember, you got to think carefully about displacement versus distance, right? Distance and displacement are not always the same thing. So in a lot of problems, we will be talking about this as a distance because it's moving in one direction. So maybe I'll clarify. Note, if object never reverses direction, delta S does equal distance. Remember that? So there are some times when we could say, what's the distance traveled? Strictly speaking, it's all about displacement, but in many of the problems we do, everything's going in one direction. You know what I'm saying? So if you hear me say distance, you're like, I thought it was displacement. Remember, there are occasions when you can use the two terms interchangeably. And this is often the case here. All right, sorry about that. I saw that note at the bottom right before I turned pages. Okay, go ahead, turn to the next page, and I've got some examples worked out, right? So I've shown it with both styles using the upper style here. I've shown this example using this style and using that style. So go ahead, I'll catch up and write it on the board. I gotta erase. Let me get some. You can look through that, chat with your neighbor if you want. Okay. All right. So imagine you're pulling a block here. So this is just an example. Right, it took so long. And you're pulling it with some rope and you've got some tension and there's some angle this way, theta, and the block is going to move this direction. Okay. So now in this case, delta S, I think I called it D in the example. That's the distance block moves to the right. All right, and we got 12 newtons and 10 degrees. So T has a magnitude of 10.0 newtons. D, the size of it was what, 3 meters or something? 3.00 meters. Okay, excuse me. Okay, so we got this, and what was our angle? 10 degrees? Sorry.
T was 12.
Oh, T was 12, the angle was 10 degrees. Okay, sorry about that. So this was 10.0 degrees, and that was 12.0 newtons. My apologies. All right, so obviously you can punch this stuff in really quick, but let's do it just to get a feel for the numbers. Work is going to be force times distance times cosine of the angle between. In this case, the force is 12.0 newtons. D is 3.00 meters. And cosine of some angle. And then we punch that in. Two things. Check degrees radians just in case when you're using your calculator. And what are the units? What's that? Yeah, joule is going to be the name of the unit. And we're going to see that a joule is a newton times a meter. All right, so just punching this in, I think I got it here. 12 times 3 times cosine of 10. What we get? 34.5 or so, or 35.5-ish. Now here's the thing. Look, there's a newton and a meter. I like to say this is a real gem of a unit. 1 Newton meter is a joule. Now keep in mind, this is spelled that way. So a joule is the new unit of energy. It's a real gem of a unit. Okay, everybody good with that? Now, later on, we're going to be doing torque problems. It turns out the units for torque oftentimes are also Newton meters, but we will call them Newton meters, right? Or maybe you've heard of foot pounds of torque. You can see that the units are the same. So unit of distance time. So it's important that when we're doing energy problems, you actually want to convert the units to joules because that tends to mean something to people. If you say Newton meters, they might think you're talking about torque. So when you're doing energy, try not to leave these at Newton meters. Good? All right. Now, if we do this the other way, just showing you that this same method works. We could get Tx and Ty. Do you agree? The components of the tension in the X and Y direction. And when I do this one, let's just get Tx real quick. What is that? 12 cosine 10. All right, 11.82. And this is going to equal some number that I don't need to compute. The units on this one should be newtons. Being a little sloppy with rounding right now. But look at this. We could also say work is equal to Tx times delta x plus Ty times delta y. Now look at this block. How much is it going up and down? 0. So that's why we could do this the same way, just showing you the two methods work. Over here, the change in x, that's 3.00 meters. Shocking. When you plug in 12, this times 3, you're going to get exactly the same number. Is everybody okay? Those are the two main styles of calculating this. They work great. One's not better than the other. Why are we doing this? We're learning a new technique to solve problems. It turns out, if we use these things called work or energy, it's a lot easier to solve problems for speed. Sometimes in a problem, all you care about is how fast something is moving. If you have one of those problems, very oftentimes energy methods are so much faster than doing forces, then doing kinematics. It's just complicated. Or there are some problems where the force isn't constant. Like a spring, right? The force changes as you pull a spring. It turns out we can actually analyze problems for non-constant force very quickly using energy methods. So there's times where this technique is better than forces, better than kinematics. There are times when it's not. It's one more tool in our toolbox that we can use to analyze physics of moving objects. Got it? Let's look at problem 7.1 and do it together. All right, 7.1. Okay. I like this one because it's a good review of the last chapter too. So it's like kind of helping you as you're still going through that homework. Oh boy. Got ourselves an incline. Some angle theta. Oops, that's not very. A little better. There's a block sitting there. We're going to be pushing it with this force like this. We're going to apply this force. All right. Let's maybe put it right on the block. So there's a zombie pushing horizontally or something. All right. We're told this block is going to go up the hill. Some distance L. So the front of the block here goes to this spot. What else do we know? Coefficient of friction mu, kinetic, Okay. We've got some friction here. Mu kinetic equals mu, we're told. All right, it looks like that's what we've got. Okay, so first thing, FBD. Somebody remind me, give me one force. Am I on the right whiteboard? Okay, thanks, George. What's one force acting on this?
MG.
mg. What's another one? F, I love it. Another? Normal, which way? Yeah, kind of this way. Trying to eyeball it to keep it kind of like that. Notice a trick I'm doing. I'm not sure where I'm going to need to label stuff. So a lot of times I'll put the label kind of out past the arrowhead a little bit, which gives me room to split up my components in case I'm not sure what's going to happen. All right, what else? What's that?
Oh, friction.
Oh, friction. Which way?
Down the ramp.
Down the ramp. Good. Okay, so there's going to be some friction here. What else? Is that it? What's that? Oh, coordinate system? Okay, which one do you want to use? Is this block accelerating or not, or do we know? When you read the problem, can we tell if this block is accelerating or not? I can't tell. If you can't tell if it's accelerating or not, what should we do? Should we assume it's not accelerating or assume it is accelerating? Which is the safer way to proceed? We should assume it is accelerating because that's valid even if you set A equal to 0 later, right? If you assume it's not accelerating, almost certainly all of our work is wrong. So if in doubt, assume it's accelerating. Which way? It doesn't matter, right? You could say it's accelerating up, and if you get a negative answer, that just means it was accelerating down instead, right? So let's just pick something. X, Y, and accelerating this way. Now, the reason I brought up this acceleration is, do you agree that if it is accelerating, it's a lot easier to use the rotated coordinate system because we have 1, 2, 3 vectors lining up? So that's kind of why I thought to do that. All right, so based off that, remember, right angle opposite the original vector. So up here on this force, check this one out. Is this correct or not? Is the right angle opposite the original vector? Is this correct?
Yes.
Or, yes, that's correct. Did that make sense?
Mhm.
So this, right, you're looking for those right angles. Now I could go back to my original picture and kind of just draw some lines around to help me figure out the angles. This is why we do a free body diagram separate, right? You do your geometry on one picture, the rest of the work over here. What's this angle? So what's this angle? So what's this angle here? What's this angle? Theta. And then every other, right? Theta, 90 minus theta. So now I got my angles. Is that good? Did I do that too quickly or is everybody okay with that? Basically, you get one of those angles in there and then every other one is theta or 90 minus. It's a good trick. All right. This side's going to be what? mg cos, mg sine. So for this problem, you agree the normal force is mg cosine theta or not? Is n mg cos? Is the acceleration 0 in this direction? Yes.
You have to add the.
Yes, people forget to add this one, right? So don't forget, sometimes there's more than n and mg cos. In particular, what's this side? Is that f cos or f sine? F sine. And now just to make this look a little better, I see I could move my label down just to right there, so I have some room. Follow all that? It's a good FBD to know for test day, right? A lot of times I'll do this where I'll stick in a horizontal force on an incline just to see if you remember how to get all the angles right. So make sure you know how to do this one. All right. Out of all this, I guess we can write some force equations. Is that what we're supposed to do next? Oh, determine expression for the normal force. So we're supposed to get N. That's part B. All right, which force equation should I write? The vertical or the horizontal to get N? The X or the Y, I mean. Yeah, Y. Okay, so in this case, somebody give me that equation. Sum of forces in the Y, what do I get?
N minus AG cos minus F sine.
That one's green, I think, isn't it? Color code it. F sine, you said? Equals what?
This is how it's.
Yep. Good job. Okay. And then I just want to come over and check. Does everybody agree why this F sine theta? Think about it. When you push horizontally, you're kind of making the block dig into the ramp a little bit, right? So it makes sense that the normal force has to be bigger than normal, right? If you just have normal force equals mg cosine theta, that's just the block sitting on an incline. Now we're kind of shoving it downwards a little bit relative to the incline. It makes sense the normal force has to be bigger. In fact, we can see that the normal force is mg cos plus a little bit, plus F sine theta in this case. All right, that's cool. That's part B. Part C, what's an expression for the frictional force? In this problem, I want the frictional force. What condition applies? Is it mu kinetic, mu static? Yeah, exactly. Don't overthink this. Isn't that just F equals mu kinetic times the normal force for this problem? Which we said mu kinetic was just mu for this problem, so we could just use mu n. All right, so that's the frictional force. Now I know this seems like we're not doing anything new. We will be doing something new in just a minute. And it's part D. I want the work done by each force now. Let's go over here to the next board. Okay. I want the work done by force capital F. You're going to see me label it like this. So when we're doing work problems, a lot of times I'll draw the capital W, clearly bigger than a lowercase w, and I'll put a subscript for which force I'm talking about. So this is the work done by force capital F. All right. So in this case, well, what do you guys want to do? Which of those types of calculations? Is this force a constant, do you think? I'm assuming it's a constant force. Let's put that assumption in. If that force is a constant, what's the easiest way to calculate the work? What was the equation we used a minute ago?
FD cosine.
FD cosine. Okay, that sounds good. F D cosine of some angle. Now, for me, I think the best thing to do is to draw a tiny little picture each time. You don't have to get these questions right, but I feel like you're right. You're going to be happier if you do what I do here, at least for a few weeks, okay? At least until test 1 or the final. Draw a picture of capital F in the direction it goes. In the real world, no weird rotated crap. Now, draw a picture of which way the object goes. Which way is the object going here? Up the ramp, right? So draw that in here. And I know this seems silly, but in this problem, it helps me clarify, okay, for this problem, D is L up the rank. And now I can see what's the angle in between. Is it 0? Is it 90? Is it 180? Or is it theta?
Theta.
Theta. So don't overthink it. In this one, it's really easy to get the work. The work is F L cosine theta, and that's the answer. Got it? Now, if you draw this picture every time, you're probably not going to screw this up. If you stop drawing the picture, you're probably going to screw up about 10% of the time. I know that seems silly, but just trust me. Draw the picture for a while until you stop messing up. Okay? Or just draw it for forever. That's probably what you should do. Okay, E. Let's do part E. Work done by gravity. I'm going to say that's the work done by mg, because that's the force. Okay? Is gravity going to be a constant force for this problem? Yeah. Now, if we were going into outer space, that would be trickier because your weight would change, right? Your mass wouldn't, but your weight might. All right, in this case, it's going to be the force, mg, times the distance, times cosine of some angle, right? In this case, let's draw our picture. mg is straight down. You're going this way up the ramp, distance L. What's the angle between?
90 plus theta.
90 plus theta. That's not fun, is it? Does anybody here have the plus angle tricks memorized for sines and cosines?
Is it just like sine?
What's that?
Is that sine?
I think it is. Yes, but here's the deal. I'm going to show you another way. This is why we might want to know the other ones. How about I just say this? Work due to mg, we could also say that's force in the y direction times delta y, and then we don't have to think so much. You see what I'm saying? Because I don't remember these trig identities off the top of my head. And I think it might actually be negative. And you'll see why in just a second. So in this case, the force in the y direction is negative mg, right? It's downwards mg. What's the change in the y direction? Well, if I go this way, distance L, and this is theta, how much am I going upwards? L sine theta. And do you see the minus sign that you missed with your guess? And I'm right there with you. I thought it was sine theta too, and then I'm like, wait a minute, it doesn't work. So notice having both styles at your disposal is occasionally useful, so we can avoid having to look up trig identities. Is that good? All right, so out of all this, the work done by the gravity ends up being minus mgl sine theta. In the real world, you'd look that up on Wolfram Alpha or something, right? So whatever, that's fine. Okay, F. What's next? The work done by the frictional force. Notice how I stopped writing theta in here? I started writing angle, right? So what happens is the most common mistake students make is they think every angle in the work problem is theta for some reason. So if you start writing angle and then checking if it's theta or not with the picture, you'll get these right. That's what I'm trying to show you here. I don't know if that's coming through. Okay, let's draw our picture. Which way does friction point? Show me with your hand. Down. Which way are we moving relative to that? Got it. Okay. So we've got friction was down the plane. We're moving up the plane, and D in this problem equals L, whatever. Who cares? What's the angle? 180. And that's not theta. It's not, isn't that interesting? Every single one of these has a different angle. Have you noticed that? We had a 90 plus, we had a theta, now we get a 180. All right. Well, what's the work done by friction? I know the frictional force was mu mg cosine theta plus f sine theta. Do you remember that? That was the part B or C. We figured out that was the size of the frictional force, right? From right over there on one of those boards. The distance is L. What's cosine of 180? Yes. -1. So the work done by friction is ugly, but it's a negative quantity. I'm going to discuss the signs and some more at the end of this problem. But I'm going to try and highlight that minus sign here. Minus mu mg cosine theta. That's a lot of work. Okay. One more. The normal force, right? Isn't that the last force? EFG. It's going to be normal force times the distance times cosine of some angle, right? Let's draw our picture. The normal force points this way. We're traveling this way. What's the angle? Oh, sorry, I did too much. Okay, we're doing the work done by the normal force. It's force times distance times cosine of the angle between. The normal force is perpendicular to the plane. We're going up the plane. What's the angle between N and D?
90.
90. What's cosine of 90?
0.
Yeah, what? At least one of these is easy. Check this out. If you're pushing on something perpendicular to the direction it's moving, you're not going to make it go faster. You're not going to make it go slower. So you're not going to change its kinetic energy. More on that in a minute. But forces perpendicular do no work. Forces opposite the direction you move are doing negative work. Well, let's look at gravity. Gravity has a negative sign. Do you see that? Well, in this case, you're trying to lift something up. Do you think gravity would help you go faster or go slower? So it's got a negative sign on its work. So what we're going to see, and I should summarize this, and I should write this somewhere. Do this. Some summary comments about this. I haven't finished the problem yet, but some observations, I guess I'll call it. If work is less than 0, if it's negative, force tends to oppose motion. Am I still on? If I, Jules, am I still good?
Yeah, you're fine.
Okay, cool. You could think of it another way as it's slowing it down, right? So forces opposite your motion do negative work. They tend to slow you down, somehow associate those words together. So that's one bullet point. Obviously, if the opposite is true, if the work is greater than 0, it's tending to speed you up. And I'm going to say tends to speed up, right? If force is perpendicular to motion, we discovered that the work is 0. These are all some things that we're seeing, right? Work tends to be negative if it's a force that opposes your motion, tends to be positive if it's supporting your motion or speeding you up, and if it's perpendicular to the motion, the work is 0. All right, all right. I know I'm kind of slow playing this one, but so far are we getting all this? So finally, let's see what's the last part. H. Assuming the block starts from rest, use work net equals delta K to get the final speed. So I'm going to come over here to this board and finish it. All right. So now I need some space to finish all this. I guess I'm going to go right here. The idea is work net equals delta K. The work from all the forces. So that means the work done by capital F plus the work done by mg plus the work done by friction plus the work done by the normal force is equal to the net work. So this is how you could actually use this in the real world. We say, look, get the work done by each type of force somehow, some way. Add those up, that equals the change in kinetic energy. We're looking for V final in this problem. What is V initial in this problem and why?
0.
Why?
Starts at rest.
From rest, I got it. All right. This was also 0 because we figured that out a minute ago. It was perpendicular. I just want to point out, we could solve this thing for V final, right? V final should equal, well, it's going to be these things, work done by F plus work done by mg plus work done by friction, right? If I take all that and I multiply by 2 over m and take the square root, take a second to buy into that. I take this side, I multiply by 2, I divide by m, take the square root. You take all those big, long algebra expressions, shove them in, you got this. You can plug it in the computer and make the computer do the calculation. Feeling good? Okay. Main takeaways. Think about the signs of your work. Every time you have to do this, right, you don't want to screw up 1 minus sign out of 3. Usually, friction slows you down. That means usually friction should be positive, negative, or 0. Negative. Gravity should be positive work when you're going down. It should be negative work when you're going up. And normal force or tension for a ball and a string, something that's perpendicular to the motion usually does 0 work. All right? Well, it does 0 work. What do you think? Ready to try a quick concept question while I'm erasing the board? See if you could get it. Look at the top of page 5. There's kind of our summary. And I want you to look at 7.2 while I'm erasing the board. You can talk to your neighbor. It's basically just try and figure out the signs of the work. Okay, 7.2 while I erase the board. Dom or Jules, is there anything either of you care to contribute at this moment?
Draw pictures.
Draw pictures. Do you like the idea of drawing like pictures like this, or do you make students do that? Or no?
You should be drawing pictures so you know which way things are.
Yes.
It helps to see equations by themselves are just equations. Relate to the pictures. What need to relate what's going to what's going.
So don't just draw equations and assume you'll get it right. Put some pictures with it to help you understand what you're writing. It's kind of what.
Theta is different in each.
Yeah, it's not always theta.
That theta is just the general theta. It's not the
Yes.
theta that is necessarily given in the.
Yeah, just because you have a picture in I think we're on this board, right? Just because your picture has theta in it doesn't mean you end up with theta. We saw all these different cases, right? That's definitely the most common mistake students make, right? Is putting in the wrong angle. They can get a force and a distance right, but they screw up the angle, right? All right, Jules, anything you have to say or no? Okay, sounds good. All right, keep looking at 7.2 while I erase. Sorry about that. We got all these experts in here, we might as well use them, right? That's what I was thinking. Okay. And you can talk as much as you want while you're doing that problem. On Zoom, I'm still just erasing, I'm almost there. All right. We've got 2 blocks, we're pulling on the bottom one. 7.2. Pulling this way. Some horizontal surface here. No friction here. So down here, we're going to say mu is approximately equal to 0, basically negligible friction. However, there is some friction up here. So I'll say mu is not 0. Okay. Okay, the system is pulled to the right. Top block does not slide relative to lower block. So we're told does not slide relative to top block. Okay, so it's not sliding. Got it. Part A. Does friction do positive, negative, or no work on the top block? What do you think? Okay, what makes you say that, I guess, or what's your thought process? How did you get there?
Same direction as the force.
Yeah, and how did you know friction was pointing that way on it? I guess, what were you thinking?
As the bottom block sliding to the right, the top was trying to move to the left, so the friction's opposing it.
Opposing that relative motion, exactly. If there was no friction, that top block would fall off the back. If it sits still, and this would come out.
Yeah.
So absolutely, great job. So we expect on the top block, friction's actually pointing in the direction you're moving. Right? So notice, if you're moving this way, let's do the work equation really quickly for this one. What's the angle between for this problem? If force 1, 2 is this way, and you're displaced that way, what's the angle between?
0.
Exactly. So we see that the work done for the top block, I'm going to say this, F12 on top, sheesh, that's a lot, is greater than 0, right? In fact, it's going to be F12 times D. That's the work done. Okay. So that's pretty strange, but here's a case where friction does positive work. Everybody agree that it can happen in the real world? It's not often, but I just want to show you that. So then, does friction do positive, negative, or no work on the bottom block? Somebody else?
It does no work.
Which is there a frictional force on the bottom block? Yes. Yes, exactly. So that's the friction we care about. Do you agree? So which way does friction act on the bottom block?
From left.
Yeah, right. Remember, if the lower block frictions forward on the upper block frictions backwards on the lower block. But frictions is not really a verb, so pretend you didn't hear me say that. You know what I'm saying? It just works for me to say frictions, even though that's not a real word. By Newton's third law, if F12 is this way, F12 must be that way on the bottom block. Good enough? So yeah, there's negligible friction down here, but there's still the top. Well, look at it. Your distance is this way. What's the angle between for this one? What's cosine of 180? -1. So what's true about the work? Work done by friction 1,2 on bottom. Sorry, go ahead.
No, negative.
It's negative. Well, take a guess. These blocks are moving together in unison. Are they going to move the same distance or a different amount of distance? Same. So what do you think is true about this amount of negative work and this amount of positive work? They cancel. So the work net by the internal force equals 0. Got it?
I was just thinking that in systems, the internal force would cancel out, so it don't really wouldn't matter.
And I was trying to, I guess, show you that not only is that true for forces, but also true for work. And do you agree? It makes sense? So yeah, so when you're doing systems, that's convenient because that's less work you have to work out. Yeah, absolutely. So that's the point of this problem. When you have a system, you can avoid internals. All right. But let me ask you a bonus question that's not in here. Which frictional condition applies here? Is this F equals mu kinetic N or F equals mu static N? Neither. It's less than. Do you see anything in any of these words that imply it's on the verge of slipping?
No.
No. Dang. So this frictional condition is, I guess we could say F is less than or equal to mu static times the normal force, but we can't say it's equal. Do you agree? We don't know it's on the verge of slipping. The safe call is to say it's less than or equal to, or just less than.
You just know it's not slipping.
We just know that it's not slipping, so we know it's static, which means we know it's not mu k. That's basically all we know. It's not mu k. And it's got to be less than or equal to this amount. That's why sometimes this quantity, mu static n, if you've been doing some of the problems, you may have noticed I call this the maximum possible amount of friction that could be applied for a given situation. So mu Sn is the maximum possible amount of friction. In this problem, we might not need all of that to keep the block on top. Okay. So far, so good? I think it's about time for a break, but let me see what I want to do here. Let me mention this. If you look at the next problems on page 5, right, 7.3 and 7.4, you could see it's basically variations on stuff that we're doing. You have some blocks, you have some forces with angles, and what did we just say were the main things students screw up? Minus signs and angles, right? And usually they're related because you oftentimes get your minus sign from the angle. So those are pretty good problems for you to work on. Let's go ahead and take our break and we could try and handle a non-constant force next. So let's go ahead and take a break. I've got 12:06, so let's take a 10-minute break.
into it.
You already calculus 3?
Yeah.
Yeah, calculus 3. I just want to know that everyone here is at least calculus 2. You're 3 calculus 3? And you're calculus. Oh, you already finished all of it? Okay, yeah.
All right, I got a fun one for you. 7.5. It's a fun one, I think. We have a bank curve here. Is that what we have? Bank curve. Oh, yeah. That's not your favorite? No. Let's see. So let's say we have a car here on the bank curve. We're gonna model that car as a block.
Wouldn't that be your rear view?
Oh, yeah, thank you. Rear view, there we go. Obviously, there's the center of the circle here. When you're going around in a circle, which way do you accelerate?
To the center.
And then sometimes there's tangential, but we're gonna ignore that for this problem. I think we're going at constant speed, right? Says speed v, so that implies it's constant. Constant speed v. What's one force?
MG.
Mg. What's another force? What's another one? Let's say you're going hella fast. Which way would friction point?
Downwards.
Down the incline, yeah. If you're going fast, friction might be down this way. Does it say how fast we're going?
Possible without sliding.
Okay, so that means we got the friction direction right. Okay. Max possible speed without sliding to outside. What friction condition applies?
Okay.
No. How fast is the bottom of the car's wheel moving relative to the road?
No.
Remember that? We did that last time. The point of contact is actually at rest.
So static. You're static.
Yeah, and it says max possible. So is it less than or equal to, or is it equal to?
It's equal to.
Yeah, it's this max possible. It's on the verge of slipping. And remember, we don't use kinetic even though it's moving because the point of contact of the tire with the road was not, yeah. So that's why it was okay to use mu static. Okay. Quickly show me in this rear view picture here, what direction is the car moving at this instant? Show me with your finger. Right? It's going this, right? Do you agree the car is going around in a circle? So from the rear view perspective, show me again with your finger. Which way is the car moving? Just show me. Into the page, right? Is everybody cool with that? What's the work done by the normal force? Why? It's perpendicular. You know it's moving into the page. What's the angle? 90 degrees. What's the work done by the frictional force? None. What's the work done by gravity? None. So this problem would be a terrible problem to analyze using work and energy because all of the forces do no work.
That's crazy.
As you go around the circle, what should be true about the speed then? If you do no work, work net equals 0. What's the change in kinetic energy? 0. So what's your change in speed? So it's just going, so a car going around a circle at constant speed is a terrible problem to analyze with work and energy. Got it? Isn't that interesting? Sometimes all of the forces do no work because the thing doesn't change speed. If something's not changing speed, the net work is 0. Whoa! Kind of fun, right? I like that one for some reason. It just seems counterintuitive to me.
So it has to have an acceleration.
Well, so here's the thing. This can accelerate, but the direction of velocity is changing, not the speed. So if you're basically, anytime you're moving in circles at constant speed, net work is zero. That doesn't mean you don't have forces. It doesn't mean you don't have an acceleration. It just means your speed's not changing, but your direction is ever changing. So you do have A. Good? Yeah, that's weird, right? Circular motion problems are weird with work sometimes. All right, that was all that was. Okay, I'm going to start doing the work for a non-constant force. Look at 7.6 for a second and kind of look at that one. All right. All right. And for this one, I've set up a demonstration over here. I don't know if it's the greatest, but it's kind of there. And then Michael, we're right behind you. If you could scoot over that way just for a second. Let me get this out of here too. Thanks, Paul. All right, so we're looking right here at this thing. We could see that a little bit. So, and let me zoom out just a little bit. Make sure you can see. All right, so with all this crap here, get this stuff out of the background picture. So I just have a spring connecting here and a spring connecting here. It turns out if I take one of these springs off, this demonstration doesn't work very well. So I know in your book, there's only one spring. If you care, we could discuss the special things that relate to this. In this problem, these springs are actually wired in parallel. So it's like doubling the spring strength. Again, I can describe that later if you want, not right now. The point being is the idea is I can pull this thing some distance, right? And eventually it's going to settle down. So right about here, we would call this the equilibrium position, right? There's no net force on it. It tends to come back to this. Now, ideally, if you had just one spring, you would only have that condition if the spring was unstretched, right? Because as you stretch a spring more and more, you get more and more force. Maybe you've noticed this, like a rubber band, right? If you pull it back a little bit, it hurts a little. Pull it back a lot, it hurts a lot. So we're going to be talking about two different types of positions for springs. One is called equilibrium, and one is called unstretched. And they're usually the same, but not always. In this particular case, do you agree both of these springs are stretched at equilibrium? They're just stretched the same amount and they balance each other out. Or I could take one of these off. This would now be the unstretched length, right? And if I pull this thing from its unstretched, what direction is the force on this block right now? From the spring. Yeah, opposite the way it gets stretched. So you kind of have this intuition. If you pull a string, it exerts a force on you the other way. All right, so when we do this thing, we can release this thing, but do you agree this is going to be complicated? As this thing moves, do you agree the amount of tension in the spring will change? So in this problem, do you agree the force is not constant as it moves? So how can we address this? Let's look at the problem now. All right, that's kind of what we're trying to visualize here. Question?
Yes, my only question is, when you have both springs connected,
Yeah.
like tied onto the cart,
Yeah.
and when the cart started moving from one side to the other, what is equilibrium? Because does
Let's
the
talk
cart-
about it.
okay,
Let's
like, does the cart actually stop, or does it just keep shrinking in the amount of movement?
Now, yeah, this is good. Just because force is zero, does that mean motion is zero?
No.
For example, you could have no force on something, but it could already be moving. And so, in fact, this happens all the time with springs. If I could show you one more time really quick, since it's easy. Hopefully that stays on there. Right? The idea here is, watch these. This is very complicated, right? But do you agree it stops moving right over here and right over here approximately? So in this case, and its equilibrium position is actually where it's moving the fastest. What happens here is when you pull it over here, this spring is stretched so much, the force is actually a maximum. This is the force is a maximum at the point where it reverses direction.
Okay.
So the velocity is 0 for a split second, but the force is huge, so the acceleration is huge as well, right? And so there's going to be 0 velocity here, but a massive acceleration that way. Then it gets to equilibrium right at the second the force cuts out. It's been building up speed that whole time, so now it's going as fast as possible.
Okay.
And then once you pass the equilibrium, this one starts stretching. Well, now there's an acceleration this way, and this one stretched more than that one, right? So when this one stretched more than this one, it's accelerating that way. There's a force that way. It slows down. There's the maximum. And it keeps going back and forth, alternating between maximum acceleration, maximum speed, right? So max acceleration at the ends, max speed in the middle. Is that what you needed to hear?
Okay, so equilibrium is basically where
The force is balanced.
force is balanced and the speed is the highest in a way.
In this case, yes.
Okay.
Yes. Good?
Yeah.
Okay. Yeah, for this case, that's true.
Or
And
the speed can be 0 for them.
what's that?
Or the speed can be 0 for them.
Yes, and so eventually, because in real life, there's a little bit of drag, there's a little bit of friction, eventually it stumbles down to 0, and then at this point, now the speed is 0, but 0 is also the max. Because it's moving, it's not oscillating at all. Is that good?
Yes.
All right. Good. Okay, so now, springs are probably one of the trickier forces. That's why we don't start with them. I'm going to try and talk about the force from a spring for a minute before we get crazy on this. It's K. This is called a spring constant. And it depends on the amount of stretch or compression. Some springs can be compressed, right? Like the shocks on your car. And the direction is opposite the direction stretched. No one wants to write that all the time, but that's really, you kind of know this intuitively, or at least it seemed like you were okay with that when we were discussing it. The way physicists write this is negative K delta X vector. Okay. Now, to be clear, delta X is not X final minus X initial anymore. It's X final minus X unstretched, which is not necessarily X initial, right? You could start from one amount of stretch and go, do you see the subtlety here? This is not X final minus X initial, it's X minus unstretched. So a convenient thing that everybody does is in spring problems, rather than choosing your coordinate system wherever you want, we often set X un equals 0 to simplify the math. Then, if X un equals 0, and that's huge, it's important that you understand that has to be true. If this is true, then force from a spring equals minus Kx. Think about that. We can get rid of that delta. And then basically you're saying this is the position relative to unstretched or uncompressed, whichever. Got it? I'm going to take this. I know this seems silly, but for me, this was very confusing when I was an undergrad. So any questions about that so far? I'm going to show you this. Minus Kx in the I hat. Would you be okay with me writing that? If we're doing a one-dimensional problem, right, we could take the x vector and just say it's x in the I hat. So that way we can kind of get rid of this. Now think, if x is a positive number, that means you stretched it to the right and the force is to the left. If x is a negative number, that would give you a positive force. So if you stretch or compress, maybe if I draw a picture here, this is the x unstretched, and that's equal to 0. There's some parameter here, x, which is the amount you stretch this block. And so if x is a positive number, you stretch it to the right, the force would be to the negative I hat, to the left. Okay, everybody good with that? So this is just showing that mathematically this obeys what we expect and what we want in our real life modeling. Now, it turns out most books take this a step further. And I'm going to explicitly write this. The magnitude of it is just kx, where this is a distance stretched. And I'm not doing this to torture you. I'm doing this because every book you ever read will say, here, this is a position. Oh, but in this problem, it's a distance. And it's the distance it was stretched. Notice here, this is a positive number, right? It's a magnitude. Question?
Take the absolute value.
You can take the absolute value of the position to get, yeah, that's basically what you're doing, right? And again, this is all assuming x unstretched is 0. So we're forced to pick this as 0. Yeah, good? The idea is this, people. When you're doing calculus with it, you're going to want to use this vector equation so that you don't screw up your minus signs. When you're doing free body diagrams, what do we always do? We draw arrows, and then we put the magnitudes of the forces. So in a free body diagram where you're drawing a picture, you might say the size of the force is kx, all positive, absolute value. Then you could show with the arrowhead which way the force is pointing. Does that make sense? All right, I hope that works. Let's go on to 7.6 now, right? This was all the intro to 7.6, Introduction to Springs. They're very useful, okay? The work done by a spring is equal to the integral of the force vector from a spring dotted with ds. In this case, I'm going to assume we're moving left and right. In case you're wondering what ds is, ds means a tiny amount of distance in some arbitrary direction. Now for us, I could say ds is a tiny amount of arc length to the right, meaning for this particular problem, ds means dx I hat. If I was going up and down, ds might be dy j hat. Is everybody okay with that? ds is just basically if you're going the x equation, it's x I hat. If you're going the y j hat, dy. All right, let's keep rocking here. The work done by a spring is equal to the integral of kx in the negative I hat dotted with dx in the I hat, right? This was the work done, and we're assuming x unstretched equals 0 in this problem. Okay, that's why I can write the force this way. What do you get when you do this integral? From initial to final. Here's a trick. Do the dot product first. What's I hat dot I hat? I hat dot I hat. Well, negative I hat dot I hat will be -1 in this case. So I hat dot I hat is 1, and because there's a negative, it's negative. Yeah. So the dot product, let me write it like this. This part, negative I hat dot I hat equals -1. I hat dot I hat is 1, and we have a negative sign. Is that good? So that is just a constant. I'll pull that out. What's left? What do you get when you integrate kx dx? Remember, k is called a spring constant.
1/2 x squared.
Yeah, so negative 1/2 k x squared evaluated at initial and final. Agreed? In this problem, do you agree that negative sign can flip the limits? Or any problem, I guess? I could use the negative sign to flip the limits, right? So it's positive 1/2 kx squared evaluated at final and initial, which it's 1/2 k x initial squared and I just want to clarify, it's not 1/2 k x initial minus x final squared. It's not this, right? People want to get lazy and like do this for some reason. No. All right, not that. Just watch out. Don't get lazy on me. It's just this stupid looking formula. How could we check this? What do we know about work and signs? Like in particular, if work is positive, what does that tend to mean versus what if work is negative?
If work's positive, it's going in the direction of the force.
Yeah, so if it's positive, it's helping you move, it's going in the direction you're moving. If work is negative, it's against you. Well, let's think about this. Okay, if x initial is bigger than x final, what does that mean? Right? If you draw a picture here, let's say this is x unstretched, we're saying if x initial is out here and x final is right here, the work is positive. Well, think about that. This seems pretty reasonable. If you start out here, the spring pulls you back towards the center, it should be speeding you up. So if x initial is bigger than x final, the work is positive. That's great. Those of you that already took high school physics, you probably know the energy from a spring is 1/2 kx squared. Have you heard that before? Does anybody know that? If you do, you're probably really disturbed by this because it feels like it's backwards. It's not. I'll explain more about that next week or Wednesday. Okay. All right. So far, so good. Now, at this point, you could plug in some numbers and do this one. Remind me again, what do these x's mean in this equation? Is it distance? Is it position? Is it displacement? What do you think these x's mean? Based off this picture you see me drawing here. They're positions, right? They're locations. So the x initial and x final here are your locations. Relative. Notice, this is pretty cool too. What if you had negative values for x initial and x final? What would happen to the minus signs for the x initial and x final? They would go away. Well, does this make sense? Let's think. What if x initial was right here and x final was closer? Shouldn't it be speeding up? Would it still do that? Well, negative x initial gets squared. That's going to be a big positive. This would be a small. Yes, it's still positive. This works. All right. So far, so good. Just trying to show you that these equations will actually help us understand things. What is the moral of the story? Sometimes you can have a force that's changing as it moves around. You could use this calculus method to figure out the work done by that force so that you can figure out how the speed changes. There's lots of forces in the real world other than springs that are not constant. Electricity, magnetism. So this is going to be used in the next physics class all the time. Enough on that? Yes.
Is work always positive in the spring?
No. Switch it. What if you started here and ended there? Then this term would be smaller than that term. You would get negative work. It's working against you as you go outwards. It's working. Yeah, absolutely. So anytime x initial is smaller than, so we can draw that here. What if I had x initial right here and I'm moving outwards to way out here? Can you see that at all? Sorry. Would help if I drew even lower. No, sorry. Anyways,
I've got a long torsion.
there you go. You got it. So if you started out X initial right here, you'd have to be moving really fast because the spring would be working against you, trying to pull you back in. And so this makes sense there as well. Good. And that would be the same could be true if it was on the negative side because of the squares. Good. Yeah. All right. Everybody good with that? Let's see if there's anything else in here worth talking about. Okay. So I'm going to mention something there. Do you see the very last line where it says watch out? Just before problem 7.7, it says watch out for horizontal springs. Equilibrium and unstretched positions are the same. So if you have a single spring, right, like this one I was looking at down here, let's just go to it. Zoom out a little bit. Right? So let's just go to a single position like this. Right here, it's in equilibrium and it's unstretched. That's great. But what I'm saying is, if you do this vertically, right, this is unstretched right here. Am I on, Jules? Am I still on or not? How about there? No? Okay. I see. Hold on. Here we go. So now when you see this thing, I just want to point out, when you're at this vertical position, do you agree this spring is stretched right now? There you can kind of see my hand at the block. So right, unstretched would be right here. Okay, everybody see the thing that I'm trying to make you aware of? Equilibrium position is where mg and kx balance for a vertical spring. That's very different than unstretched. So just, I cannot stress that enough. Unstretched and equilibrium are not the same thing for vertical or on an angle or any of that. We'll cover that more in the next chapter. I'm going to let you work through the numbers for parts A, B, C, and D on there. Oh, I do want to mention something about the units, though, before we go on. I want to focus more on this technique of doing the calculus because I think that's the hard part. Plugging in the numbers, I'm going to trust you to do that. But let's talk about the units really quick before we go on. Yes. Oh, thanks for the camera. Wrong camera. All right. Okay. Do a quick unit check before we go on. Thanks, Jules. What are the units of force? Newtons. What are the units of X? So what units are required for the spring constant? Just in terms of newtons and meters. Don't overthink it. Newtons over meters. Just double check. You agree newtons over meters times meters gives you newtons? So the units for a spring course, the spring constant, the units for the spring constant are newtons per meter. Think about it. It's how much force you must apply to stretch the spring a given amount. So this relates to a property called stiffness, right? A stiff spring has a large value for K. It takes a lot of newtons to stretch it a meter. A very weak spring takes hardly any force to stretch it a meter. If you're curious, this spring right here that we've been using is somewhere on the order of 3 newtons per meter. It's either 3 or 6. This thing is super easy to stretch. So on your car or something, it's very different than these weak little springs. Okay, so that's just for the units, so you know what that means. All right. Notice if we summarize the work done by the spring, our result was it's 1/2 K x initial squared minus 1/2 K x final squared. And in this case, check the units really quick. What are the units of work? It's a real gem of a unit. It's a joule. A joule is the same thing as a Newton meter. Let's confirm. Newton per meter times meter squared, check. That's a joule. So these units are also consistent there. Good. Okay. All right, let's try 7.7. Go ahead and read it. I'll get the board erased. 7.7. Erasing. All right, 7.7. Let's get on the board here. Come on. We're told that the force on a bullet in a barrel of a gun is alpha x minus beta x squared. So for some reason, this is our claim that the force on a bullet, and this is just some made up formula I made. This is not necessarily realistic, but it's a start. And now I'm just going to model this right here. There's some length L for the barrel of the gun. You can imagine there's a bullet in here. We'll just call that a block. Keep it easy. Mass is M. Mass of the bullet equals M. And this is the force while it's in there. And obviously at some point, you agree afterwards, it's going to be out here flying out at some speed V. It says alpha and beta are constants. All right. V is not known, so I'll just clarify that I'm assuming it's going to be moving at the end. Be a pretty ineffective gun if it wasn't. You're right. So let's keep going here. I want to get the work done by this. In this case, do you think the work is a constant or is it not constant? Look at it. Is our value for x, do you think, is that going to be changing in this problem?
Yes.
So will the force be changing? Yes. So can I use this? Can I just say it's f sub x times delta x? Can I do this? Is that true? Does this work? No, it's not constant, not valid. We have to do the integral this time. Okay, so that's the main change. If you can recognize if a force is constant, don't do the integral. But yeah, okay, so then here, what are my limits? What's the smallest value of x?
0.
And what's the largest value?
L.
L. So in this case, we're integrating from 0 to L. Okay, let's crank this out. You're faster than me, right? Go, go, go. Oops. X. What do I get when I do the first term? X squared. Alpha x squared over 2. Yep, and I'm going to evaluate. It's worth it to do this extra step. Like you could probably jump ahead and say, oh, I know the zero limit's not going to matter here, but I want to get in that habit of doing it. And then the next one, what do we get there?
1/3 x cubed.
Yeah, beta x cubed over 3. Evaluated at 0 and L. In this case, does the zero limit drop out? Yes. So in this case, what do we get? What is it? Alpha L squared over 2 minus beta L cubed over 3. How could I check the units?
Set the individual terms of the force.
In the original equation, we used this original equation to check the units so that we could check the final answer units. Did that make sense? You may have noticed that I skipped part A, I think, right? In part A, it says, figure out the units of these terms. The whole purpose of that is so you can check it later and make sure you didn't screw up your integral, right? Did that make sense? I'm going to do this basically every test for the rest of time now, where I'll give you some equation with some constants in it. And the first step is usually check those units. So remember, if I want to get the units of this, I can check this one against the force separately from this one. Most people miss that on test 1, which kind of drove me nuts. Let's do part A really quick. Remember, when we're checking the units, we can separate these terms out like this. So what are the units of alpha? Obviously, I don't know what alpha is, but I can get the units of alpha. What is it going to be?
Force to max.
Which is newtons per meter, right? Do you agree? Units of force? Yeah. Okay, and then somebody else, what are the units for beta? Newtons over meter squared. So now, if I wanted to use that, I could check this answer. Well, I've got newtons per meter times meter squared. That's a newton meter. That's a joule. That's a unit of work. Here I've got newton per meters squared times meters cubed. Again, I get newton meters, which is a joule. I get work. So far, so good? All right. In this case, I think we've done parts A and B. Is everybody satisfied with that? This was part A, and this answer was part B. We checked the units. This was the answer to part B right here. If I want to get the speed of the bullet, what could I do?
Network equals.
Exactly. Now that we know the work, we could say work equals 1/2. Whoops, we could say, let me do it this way this time. Work equals delta K, which is K final minus K initial. Why is the initial kinetic energy 0 for this problem? What did it say? How quickly are bullets moving before you fire the trigger usually? Yeah, it's initially at rest. Didn't it say the bullet starts from rest or something? Okay. So in this case, I've run out of room. I'm going to go to the next board. Just continuing part C. We say the work is equal to 1/2 mv final squared. The initial was 0. So in this case, notice a lot of times you get this cross multiplied by 2 over m. Do you see that? We're almost always seeing 2 over m times some crap. And then you could square root it. Now you could be saying, wait, shouldn't I be worried about the plus minus sign? Sure, if you shoot the gun to the left, you'd use a minus sign. If you shoot the gun to the right, you'd use a plus sign. Good enough? And could we simplify this a little bit? Sure. But is it pretty simple already? Yes. Good? Now, I know this seems like a ridiculous problem up until this point. But I want it, right? Most of you are taking this class not because you want to do math all day, because someday you want to build something cool or do something interesting with your life. Think about this. We've just derived this equation. Let's say this was a real equation and these terms alpha and beta related to properties of the gun barrel. Well, this would give you an idea of how to adjust properties of the gun, how to design an object to optimize the speed. Maybe you want, and maybe you're like, well, if I use a longer barrel, at some point, this is going to stop working because this turn is going to get too big, right? If your gun barrel is too long, eventually the bullet's just going to be dragging against the walls, and that, right? So maybe we could use this to kind of say, well, for this particular type of bullet, in this situation with these constants alpha and beta, the longest gun barrel I should use is this or that. Point being, we're trying to analyze real life and design better products to be used by humanity. Maybe this gives you a step in that direction. That's why we were doing this problem. Good? So yeah, the algebraic work sets you up to design better products as an engineer. All right. In this case, my claim is that you should not design the barrel so long that it's slowing down the bullet. How could I find the optimum, the maximum gun barrel length?
The derivative of some salt for no?
The derivative of work, which is, how did we get to work? What did we integrate to get to work? So if I want to optimize the force, rather than taking the derivative, let's just use the force, right? Think about this. If f sub x equals 0, do you agree that's the same thing as saying the term that's pushing it forward balances the term that pushes it back? That's going to be an over-under for the length. Do you see it? So, which is basically what you said. Taking a derivative of this gets you back to the force. Does that make sense? Yeah. So in this case, what do we get? Alpha x equals beta x squared. One of the x drops out. And so what do we get? X equals what? Alpha over beta? How could I check this? Check the, and isn't it convenient that we actually figured out the units? So now we can see if this is nonsense or not. So we got newtons per meter divided by newtons per meter squared. That's newtons per meter times the reciprocal, meter squared over newtons. That's a length. So this would tell us, okay, if your gun barrel is any longer than this, we would expect the squared term to dominate, and you would be losing speed off your bullet. If the barrel is shorter than this, even that last little bit should help speed up the bullet, if this is an accurate force model. Cool? I think that's, we've finished that problem. Not much else you could say there. Oh, here's an interesting one. What's the force on the bullet when x equals 0 for this problem? 0, right? So that means this bullet would never start moving. So it's a little bit fictitious, right? I guess what I'm assuming here is this is the force on the bullet if you have some small non-zero x to start, right? So again, this is a non-physical problem. I wanted to make it easy to do and kind of think about, but to be clear, this model doesn't make a lot of sense in my opinion. It was an easy one to start, and it's an easy problem to learn for. Whoops. What I'm saying here is this seems pretty silly, right? Maybe I should have put a constant in here, right? Just so there'd be some initial force, because if you put in x equals 0, the bullet would have no force on it. All right, so apologies if this seems weird because of that, now that I told you it, you didn't notice that before, but whatever. It's good practice. Another one for you to practice is 7.8, okay? So there's another one. This kind of stuff can show up in electronic structures. There's all kinds of information about that. You can read that there. All right. I want to end today by talking about a new concept called power, which relates to both of these. If you want, you could look at the top of page 8 really quick. Okay, I'm gonna erase the board. Silly little problem, but it got the job done.
It's your set.
Yo, I'm listening. I'm just erasing.
If the United States opens on another program like the Manhattan Project, would you join?
And miss the chance to grade all these labs? Well, you know what? I would worry about it when it happens, right? How about that? It's a very uncommittal answer, non-committal answer. Yeah, I just, I don't know. I haven't thought about it at all, and I don't know. So,
You know, like if World War III happened.
I know. Well, if World War III happens, I might go surfing or something. What the heck, right? We'll see what happens, you know? It might be my last chance. All right, so I was actually in Hawaii during that missile scare. Do you remember that? You guys might not. I was in Hawaii and I got woken up by a text that says inbound ICBM, seek shelter immediately. The entire island thought there was a nuclear war started. It was back when Trump was talking about his big red button being bigger than Korea's. Anyways, so there was a plausible chance, like we were all like, man, I remember thinking on my flight to Hawaii, this could be the start of World War III. And then we get this text message. So I'm like, well, let's go to the beach. So that's what I would do. I'm pretty sure, because I've been in that situation and that's what I thought. But everybody else is like, oh, let's watch TV. I'd just say, let's go to the beach. That said, now you know. Okay. Okay, so power. All right, power, DEDT. Change in energy over time. Sometimes you'll see it written like this, work over time, right? Because work relates to change in energy. That's one of the things we've seen. All right, and I think actually this is sometimes average power, so I'll put an approximate here. Average. Now notice I use a puffy P, right? Just a quick summary of the P's that we have. This is rho, that's density. This is lowercase p, that's momentum. Right? This script P is going to be power. And a capital P is going to be pressure. So I'm not trying to be mean here. Every P looking symbol that we have is different. And so it's important that you write them differently. This is how I chose to do it. That doesn't make it the right way to do it. If you're not sure, if in doubt, there's many problems that have momentum, power, pressure, and density all involved in them. So it's critical that we clarify that if it's ever unclear. My apologies if you don't like that. It's just, I don't know what else to do. That's all of our letter P's. All right. There's another formula we have for power. Instantaneous. And that's going to be force. Got it, with velocity. So that's another way. And you can kind of see all these are related, right? Work is something like force times distance. Well, if you took a derivative of that, you get a force dotted with velocity. Maybe that makes sense. All right. What do I want to say about this? I think let's try starting with 7.10 because I really like this problem and I feel we could kind of walk through all of it together. So we're looking on page 8, 7.10, and I think we're going to finish with that one today. In that problem, we're told there's a position equation. Let's say you're watching a video and you do some tracker and you do a model and it seems to fit this strange behavior for whatever reason. What's that? Oh, thank you. Thanks, Jules. Forgot. Come on, there we go. Okay. What units are assumed? Let's do a quick unit check. What units are assumed on the number 2, even though I didn't write them? Meters. What units are assumed on the number -3? Meters over seconds cubed. Everybody take a second, make sure you feel good with that. Just imagine if you plug in seconds cubed, I get meters. This makes sense. Okay. What's part B ask us to do? Okay, so let's do that. How do I get the velocity as a function of time? Okay, so what's v of t for this one? Derivative of 2 is going to drop out. So what do I get? Negative
-9 t squared.
-9. Do you agree the units on this 9? What are the units on that 9? Exactly. It's the units of 3 times a constant that had no unit. So it should still be the same as this. Did the units check? Meters per second cubed times second squared gives me meters per second. Okay, how do I get A of t? Another derivative. It's going to be what? -18 t. The units look good. Okay, that's part B. What's part C? How do you get the net force on an object from this? What's the most famous physics equation you know? What do we have?
Acceleration.
Do we know what m is in the problem?
Yes.
Yes. It's 0.25, I think. Which is 1/4, so that should be what, 4.5 negative? Did I screw that up? Double check, I think that's right. Times t. And again, what are the units now? This is getting kind of tricky, do you agree? This had kilograms. This one has units of meters per second cubed. So to be clear, this number now has units of kilograms, meter per second cubed. It's always a good idea to kind of, it's so much easier to do the problems without the units in there, but we got to keep an eye on them in case we have to explain to somebody else what they mean. When I multiply by a second, I get a kilogram times a meter per second squared. That's like the units of an mg. That's a force. All right, next. I want the instantaneous power at 2 seconds. So D. I want instantaneous power at 2.00 seconds. What equation do we have for instantaneous power? Power equals force dot velocity. And I'm going to say dot just because there's different ways to multiply vectors, which in this case, if something's moving in one direction, that's force x times vx plus force y, vy plus, yeah, etc. But in this case, do I know the force at 2 seconds? Or could I figure it out? Yeah, it's just negative 4.50 t, and I can plug in 2.00 seconds, right? What's that? It's a negative force, yes, negative force. Do you agree? We see this force is working against you, right? So you're moving to the right, or wait, oh, let's see, in this case, oh, actually, you're moving to the left. Ooh, interesting. Well, we'll see how this works out. What's the velocity? So see what I was like, oh, whoops, the minus signs are going to cancel, aren't they? Well, this is interesting. Your force is to the left, but you're also moving left, so you should be speeding up, so it's okay. Positive power. Okay, I'll just put an inst here, just so we're clear, this is instantaneous. So I think this is showing you one way you could calculate this stuff. If you know the motion of a particle, you can figure out its force, its velocity, you can get the power at any instant from basically making a video of it, right? If you get a video of something, you can figure out its x as a function of time, figure out the force on it as a function of time from that and its mass, and crank this out. That would also need to be 2.00 seconds. So far, so good? One last one. The average power. I just wanted to clarify why this is different. Power average between 0 and 2.00 seconds. The way you calculate that is, let's do it like this. Work over time. Well, that would be change in kinetic energy over time. Well, that would be 1/2 mass the final squared minus 1/2 mass the initial squared all over 2.00 seconds. And this number is not going to match that number. Think about it. You could come into here, you could plug in V of 0 for this one. Here, you could plug in V of 2.00 seconds, get a bunch of numbers and plug these in, and you would find that the average power is not the same as the power at any one instant. And you can tell, right? If you're exerting this force, the force is going up and the velocity is going up. We're exerting a lot more power towards the end of this than we are at the beginning. That's it. All right, so far so good. So it's time to go. If you want to get out of here, that's cool. I'll wrap this up. We basically finished chapter 7. What I know, this is crazy. What I'm going to teach you next class, I didn't want to tell you this right away. I'm going to show you some tricks to do this even faster in the next chapter. Instead of trying to use everything with work all the time, I'm going to show you how to use energy, and we'll discuss that more in the next class. So yeah, go ahead and finish that up at home, and yeah, I'll see you on class on Wednesday. All right.